Professor Christos Mantoulidis from Rice University. And he is also the recipient of Frontiers of Science Award of this Congress. Today he will give us a talk on minimal surfaces and the Allen Cahn equation on three manifolds. Let's welcome.
Thank you for the welcome, and thank you for sticking it out until this afternoon to come to the talk. It has been a great conference. It's a great pleasure to be here. Very wonderfully organized. So today I'll talk about a paper with Otis Chodos that won one of the FSA awards, and it'll be about the minimal surfaces and the Allen Cahn equation. And the main theorem that I'll talk about, at least for the paper, is concerned about the three-dimensional case. This is my second ever slideshow talk. I thought there would be no blackboard, so if I make all the rookie slide mistakes, I'm sorry. Okay, so let me just, for the people in the audience who are not experts, let me just tell you about what I generally work on. So my main object of study are minimals of manifolds, which are variational generalizations of the notions of geodesics in Riemannian manifolds. And let me just write a cheat sheet here of these kinds of perhaps background knowledge that is good to have if you don't have it. So I will eventually want to consider embedded minimal submanifolds, which are closed, meaning compact without boundary. But I'll also want to consider multiples of these things and finite unions. And so there might be intersections. And so for the purposes of this talk, let me set everything up in one way that generalizes all these things, which would be like closed immersed minimal surfaces. And so in that context, you can think of their definition as being, so you have a k-dimensional sigma in an n-dimensional Riemannian manifold M, which is closed and immersed, but immersed will be assumed everywhere. So this will be called minimal, provided for every normal variation. So for every section of the normal bundle of sigma, the derivative of the area is 0. So it's to first order, the area doesn't change under perturbations. So the area of the graph over sigma of the vector field, the normal vector field t times x, is at time t equals 0 is 0. So here are a couple of pictures. So it could be a local minimum. It might not be a local minimum. That's totally fine. And we will mostly have to actually worry about the non-local minimum case later in the talk. So for that, it's also important to have the notion of how many directions do I have where I'm not a local minimum in. So let me just remind you of these couple of definitions. So for a minimal surface, you have the notion of the Morse index, which you should think of as the maximum number of directions I can push my surface toward so that my area decreases the second order. So this will be the maximum among all the dimensions of subspaces V of this space, such that this second derivative instead of the first derivative at time t equals 0 is negative for every non-trivial variation x in V minus the trivial variation. So in these two pictures, so okay, let's go back to here to the non-cheat sheet part. So in this picture, and then let's say this picture, and let's pretend that the picture on the right is just a round sphere, just so we can have something concrete in mind. So let's say this here is a codimension 1 equator in a round sphere. And this is maybe some kind of a hyperbolic manifold and some totally geodesic hypersurface. Then here, I'm a local minimum, so I cannot have negative directions for my second derivative. So here, the index of sigma will be 0. And these kinds of things you will hear me refer to as stable. later in the talk. So if I talk about a stable critical point, a stable minimal surface, I will mean that it has index 0. Here, my index is not 0, because if you take an equator and just slide it in this direction, you get a second order decrease in area. And a computation shows that this is the only direction of decrease in area if you're in codimension 1. And I will also need one more notion, which is what about pushing in direction so that to second order my area stays constant, and that's the nullity of a minimal surface. So that's the maximum number among all dimensions of subspaces V such that the second order derivative is equal to 0 for all x in my space of deformations. So if I've set up everything correctly, let's say in this hyperbolic metric here, then my nullity here would be 0. And this kind of situation I will refer to later as this minimal surface here being non-degenerate. Whereas in the sphere, I have tons of degenerate directions because of the ambient symmetries. And so this is going to be a degenerate example. In fact, you can compute that if you're in the n sphere, the nullity of an equator is equal to n. As a toy example, take a 2-sphere, take an actual one-dimensional equator, then this rotation and that rotation are both nullity directions, and there's nothing else. So this is a degenerate example. Okay. So I want to talk about, maybe as a selling point, even though at a basic science conference you shouldn't be doing any selling, but minimal surfaces are useful. I mean, they're beautiful in and of themselves, but they've also turned out to be extremely useful in answering questions that a priori have nothing to do with minimal surfaces. So I've listed a few of them, perhaps more historically. One original beautiful application, more so in the harmonic mapping vein, but you can view these as branched minimal surfaces, is the Frankel conjecture, where Su and Yao's proof of the Frankel conjecture. So let me just write it here in case you haven't seen these kind of things before. So the Frankel conjecture was about proving that if you have a closed, meaning compact without boundary, Kähler manifold with positive bisectional curvature, then it must be biholomorphic to CPN. And the main, from my perspective, the main analytic step in the proof was to capture the second homotopy groups of these manifolds by area minimizing spheres, or let's say energy minimizing harmonic maps, but area minimizing spheres. So here the point was to represent pi2 of M via minimizing, therefore stable spheres. Then you had the Garrosh conjecture, which was about the fact that a metric on a 3 torus cannot have everywhere positive scalar curvature. And the main step in the 3-dimensional case was to represent homotopically area minimizing incompressible surfaces. So find minimizing, homotopically minimizing incompressible surfaces. And in the higher dimensional world, the main point was finding area minimizing representatives of codimension 1 homology classes. So again, an area minimization. The positive mass conjecture was, or today is understood as being a cousin of this after a very nice trick of Joachim Lohkamp. So again, this requires producing minimizing representatives. But I've been minimizing everywhere, but you don't always minimize. So one of the ways that was shown that 3D Ricci flow with surgery becomes extinct in finite time on an S3, where you cannot minimize anymore. There's no topology in which to minimize. Then Kolding-Minikosi's approach to showing that 3D Ricci flow with surgery goes extinct is to keep track of certain minimal two spheres and showing that their area must go to 0 in finite time under the Ricci flow. And these are not constructed a priori by minimization. So you will have to find more ways to construct minimal surfaces. So Ricci flow with surgery, you have non-minimizing spheres being of importance. All right. So the various classical constructions, the various classical variational constructions of minimal surfaces are in the two-dimensional case. You can have the work of Sachs and Uhlenbeck and Shane Yao, which came from more of the harmonic mapping approach, and then using some ideas from Teichmüller theory to construct minimizing surfaces, and then in a homotopy sense. And then in the isotopy sense, in 3 dimensions, you have the result of Meek, Simon, and Yao. And then to prove certain regularity when you're in 3 dimensions, in translating from the harmonic mapping approach, the minimal surface approach, you have some very nice regularity theorems of Osterman and Gulliver. When you want to produce hypersurfaces by minimizing in integral homology classes, I won't be using any of this, so I'm just going through it fast. You have the work of Federer and Fleming, and then the regularity theory of Fleming, Almgren, DeGiorgi, and Simons for the interior case that is important. But in the non-minimizing approach, such as here, so okay, conversely to here, you can, you have, what do you mean? What does I mean by minimizing? You just pick some initial representative and you just try to find something that is optimal in whatever constraint set you're interested in. Well, so for example, here you would slide it into something that is optimal. But if you're in something like a sphere, if you start with some representative here, if you were to try to slide this so that it becomes optimal, then you go extinct. Like there's nothing that you will converge to. And so this minimization approach doesn't work in a trivial way here in a sphere. So there are these beautiful alternative approaches called min-max constructions, where instead of doing this direct minimization, what you should be doing is looking at all possible ways to, let's say, sweep out your whole ambient manifold by submanifolds, for example, codimension-one hypersurfaces, non-minimal. And when you have a sweep out like this, find whichever element in the sweep out has the largest area. So in the more dark gray, I've highlighted one that has the largest area. And among all possible sweep outs, try to minimize that largest possible area. And with a lot of work, you will get that this converges to a not a minimizing, but a minimal codimension-one surface. In higher codimensions, you get terrible regularity, so that's why I'm focusing on hypersurfaces. And this was carried out by, I mean, we have had major advances in this, but this was initially carried out by Almgren and Pitts, and that's what we call the Almgren-Pitts theory, which was then improved regularity-wise by Shane and Simon. Then we have the Simon-Smith result about a more topologically constrained, when you want to get more topological answers, min-max theory in 3D, which was written in a different way by Kolding and Delelis, and Delelis and Tasnadi had a higher dimensional version of the Almgren-Pitts theory. Marcus and Nevis recently, we heard talks today about how they just pushed min-max theory a lot farther to give us even more geometric applications. And Shinzo and Daniel Katover have made, again, additional significant advances in min-max theory. So this has been a very, very beautiful and active field in the past decade especially. There aren't, I mean, these are not the only constructions, the min-max construction and the minimization that I told you. So earlier today, we heard from Tristan Riviere, who had a different intrinsic mapping approach to carrying out min-max when you have a two-dimensional object in the domain. So if you want to produce minimal surfaces. And there's other beautiful recent very successful approach to producing minimal surfaces via eigenvalue optimization, and some references are written there. Okay, so there's lots of ways to construct minimal surfaces, and today I'll talk about yet another one. Okay, so that's what my goal is for today. Oh, and these are the variational approaches, but there are non-variational approaches via gluing, and that's another beautiful approach that it's kind of orthogonal to what I'm talking about today, so that's why I don't have a slide on that. Okay, so what are we going to be doing today? So we want to find a different way to construct minimal codimension one submanifolds or minimal hypersurfaces. So we're going to be trying to construct such minimal hypersurfaces as limits of nodal sets, limits in a suitable topology, of nodal sets of functions that are solutions to certain elliptic PDE. Okay? So the picture that I have over there is my ambient manifold is here in gray, and I will define some operator E with some parameter epsilon. And this operator is agnostic of any minimal surface in here. It's an ambient operator. I will look for critical points of this operator. Here's one such. And I will, in sending this parameter of the operator epsilon to 0, I will make it more and more degenerate. And I will keep track of how these solutions behave. And the heuristic, that I'll make more precise, is that as I send epsilon to 0, these functions will concentrate toward the minimal. This is what this is supposed to mean. These functions, these critical points, will concentrate as epsilon goes to 0 towards some minimal surface, in the sense that their nodal sets will converge in Hausdorff to some eventual minimal surface. And away from this minimal surface, my functions will be approximately +1 on a side, -1 on another side. And the energy, this epsilon, will converge, this E sub epsilon will converge to the area of this minimal submanifold. Okay? So let's make this a little bit more precise. So let me keep the picture that I had there, here. Here's my mg. On mg, I will have my energy functional, which takes smooth functions and spits out numbers. So E epsilon of u will be an integral of some Dirichlet energy plus a term involving something that is called a double well potential, where this w, as I'm writing there, is a function from R to R, and in the standard case is taken to be, it's not important for our purposes that it's this function. In fact, later in the talk I will have to change this function. But for the most cases, the standard double well potential take is this guy. And I think the reason we call it W is because it's supposed to look like a W for the proofs to work out. So you need a function that looks like this, where it has two global minima at plus and minus 1, and a non-degenerate in between critical point at 0. And for some applications, you need it to be even. So this function satisfies all these constraints. So it's not really important that it be this function, just something that qualitatively looks like this. So once you have a double well potential like this, which for minimization purposes, if you look at something like this, clearly this favors constant functions because this will make that be 0, and constant functions that are plus or minus 1 because that will make this term be 0. And by virtue of this critical point here, it also favors that your critical points don't meander too long around the value 0, and that's why in the previous picture we can get this behavior where once you know where your level set is, then away from the level set, some basic maximum principles will tell you that you're going very quickly to plus and minus 1. So this is our functional, and we will be talking about Allen Cahn epsilon solutions. So we will say that an Allen Cahn epsilon solution, u sub epsilon, is a smooth function which is a critical point for this. So in that sense, for each deformation zeta, we have that ddt at t equals 0 of the energy u epsilon plus t zeta is 0. And this is equivalent to an elliptic PDE, of course. The Euler-Lagrange equation would be epsilon Laplace u equals w prime of u divided by epsilon. This is the Laplace with respect to the background metric G. So this is, as I was saying, this is an elliptic PDE, and it becomes more and more degenerate when I send epsilon to 0. So that's the setup, and my goal is eventually to tell you about theorems that prove that if I have such solutions, then under certain appropriate a priori assumptions, these solutions will converge in some sense to a minimal hypersurface. And the sense that I will be using throughout this talk is the following. So the sense will be by the way, I drew a manifold with no minimal surface here to emphasize that this operator isn't built around a minimal surface. It's just an operator on the manifold. Okay? But what the various theorems we will see will prove is that when you take suitable limits, then what will happen is that the nodal sets of your solutions, as some epsilon I goes to 0, will converge in the Hausdorff sense to a minimal surface, and the energies will converge to the area of the minimal surface. There's actually a secret multiplicative factor here, but I'm throwing that away. Now, there is this issue that will occur many, many times, and it's the main point of this talk, is that the worry is that you could have convergence to a minimal surface, perhaps with multiplicity. So you could have some nodal sets that are doing something like this. And so what I want to allow here is I want my minimal surface here that I'm converging to be allowed to have multiplicity and also to be allowed to have various components. Okay? That's why I was working in the class of immersed surfaces earlier. So these here are the nodal sets. And they're becoming more and more concentrated in a small neighborhood of size little o of 1 around some eventual minimal hypersurface. So these two conditions are what I mean by this converging to sigma. Okay? All right. So let's have some sanity checks. So one sanity check is if we do have a minimal surface, a minimal hypersurface in a manifold, can we obtain it as such a limit? So a first important result in that direction was due to Frank Picard and Manuel Ridore, who proved that in the case where you have an embedded minimal hypersurface sigma, which is assumed to be non-degenerate. Remember, non-degenerate means the nullity is 0. So there are no trivial directions to the second order derivative. Then you can always construct some set of solutions u epsilon for all small enough epsilon, which converge with multiplicity-one to that surface sigma. So it will look a little bit like, perhaps like this. Okay, that's great. However, there's this very interesting feature of the Allen Cahn equation, which in one way or another is what I've been trying to exploit for various years, is that there's actually a little bit more rigidity in the Allen Cahn equation than in the minimal surface equation. And I don't have a theorem that this is a meta idea. And one of the ways in which that rigidity manifests itself, one of the many ways, is, for example, that you cannot have all minimal hypersurfaces be obtained as such limits. So there are examples where they are not obtainable. And let me draw you some pictures to show you what I mean by some kind of a rigidity here. For example, if you take something that has an ambient S1 symmetry, so something that is a product with an S1, an isometric product with an S1, then by a silly, not a silly, but by a straightforward minimization argument, if you have, these anti-symmetric antipodal slices, which are certainly totally geodesic and therefore minimal, by a minimization argument, you can indeed recover this as an Allen Cahn solution. That's fine. However, if you were to take non-antipodal copies, so if you were to have something like one is here and the other one is here, then you can prove that there is no sequence of Allen Cahn solutions that converge to this configuration with any kind of multiplicity. You can't play around in any way to get this kind of convergence. So what happens is that for easy reasons, you could not have an odd number, and I can also do the same thing for an even number, any even number, but this was the easiest to draw. Yeah, so if you were to have something with an ambient S1 symmetry, and if you have Allen Cahn solutions converging to it, then a posteriori, it must be an even number of copies, and they must be equidistant under the S1, keeping track of the S1 fiber. Yeah. That's a great question. I'll come to that. That's one of the conjectures that got some attention for this paper. The answer is yes. Yes. Well, I don't know if they're non-degenerate for all metrics, but for generic metrics, they're non-degenerate. But I would have to think further about if they're non-degenerate always for bumpy metrics. Oh, let me come back to that. And there's also examples where you can do this with one copy of the surface. This is what Jinwen Chen and Pedro Gaspar did, which is another illustration of what goes wrong. You can have like a flat product factor, which you can sort of smooth out here and have two copies. So this is antipodally symmetric. This is Z2 symmetric under flipping it around. And what they proved is that you can only have this kind of behavior here, but you cannot have an off-centered thing happening. So if you cannot have this off-centered behavior happening. So if you converge to a single minimal surface, then this single minimal surface in this product region must be in the middle. So there's some kind of these interfaces are, in a meta sense, aware of each other, and they can't just be anywhere. And there's various other ways in which one can try to exploit things for the Allen Cahn equation. Okay. Now, in all the pictures that I have, so I'll come back to this. Okay, so in these pictures that I drew for you, I started with minimal hypersurfaces and I constructed Allen Cahn solutions out of them. But if you want to construct new minimal surfaces, then that doesn't work. You can't start from minimal surfaces and construct Allen Cahn's and then obtain new minimal surfaces. You have to start from Allen Cahn solutions that are obtained in a different way and get limits that are minimal surfaces. So this is obtained by this very beautiful min-max scheme of Pedro Gaspar and Marco Guaraco, which is the Allen Cahn version of the Ambrun-Pitts min-max scheme in a certain sense. But I'm not saying this in a negative way for their paper, it's just significantly shorter than the Ambrun-Pitts setup. Because here you have a lot better of a Palais-Smale theory that does away with many of the difficulties that you would encounter in the Ambrun-Pitts theory. So there's an order of magnitude difference in terms of the length of these min-max theories. So this min-max theory, but essentially, I don't want to go into the full details, but what it does say is that there's the obvious way of constructing critical points, which is to minimize, and that is what corresponds to doing a min-max construction with parameter p equals to 0. So when you do a p equals 0 min-max, so they define these min-max energies. So this is the p parameter min-max energy of E sub epsilon, and they prove on a manifold. And for example, C epsilon at 0 corresponds to minimizing the functional. And as I was telling you earlier, that functional likes to be minimized when you have the constant function plus 1 and the constant function minus 1. Then, the one parameter min-max is what you might have seen in different settings as what we call the amount and pass construction. Energy from starting from a critical point, the minimizer u equals minus 1, going to the minimizer u equals plus 1, seeing among all paths that possibly go from one to the other, finding the path which has the least maximum value. That's this value, and then they could define more and more complicated versions of these. And for each parameter p, they can construct an Allen Cahn epsilon solution u sub epsilon sub p, which attains this value, and whose Morse index, which is defined in exactly the analogous way from here. I won't write it again. So it's the number of negative directions and the number of 0 directions for the nullity. So with their constructions, they prove that the Morse index of this critical point they obtain is at most as big as the number of parameters p. And if you add its nullity, then it's at least as big as the number of parameters p. And they also proved some additional things that will be a little bit, I won't be using too much of, but if you send epsilon to 0, which is what we are doing a lot of, so this is what we're keeping track of, what are these energies doing when you send epsilon to 0? They're proving that this converges to some number. And in fact, this number, you will see what this number is. They also had it here, but there wasn't enough space. But I'll tell you. And the way these numbers grow will be important later in the talk. This is a Weyl type law for the spectrum of the operator behind this energy. And that will be important too. But in any case, we have this new problem, not the area problem, but this E epsilon energy, the Allen Cahn energy problem. And this too has a beautiful min-max construction with very important Weyl laws. So let's see what the limits of this construction are. So here's the theorem, which was completed in various stages. It was initially proven with some weaker assumptions by Hutchinson and weaker assumptions here by Hutchinson and Tonegawa. Then Tonegawa and Wicker-Masakera added some assumptions and got improved conclusions. Marco Guaracco did this in the manifold setting, and Pedro Gaspar proved something else that I'll mention here. But the idea is, let's say that somebody gives you, either via min-max or whichever way, let's suppose that somebody gives you, for a manifold with dimensions between 3 and 7, some sequence of epsilons going to 0, epsilon I is going to 0, some epsilon I Allen Cahn solutions, and let's assume that the solutions that were given to you have uniform energy bounds and uniform Morse index bounds. Okay? Doesn't matter how these were given to you. It could have been from min-max. So this would have happened in this min-max construction for a fixed parameter p. Now, once you have these, then you can pass to limits by sending epsilon to 0. And what will happen is that these u epsilon i's will concentrate as epsilon goes to 0 around disjoint embedded minimal surfaces, but possibly with some multiplicities, m1 through mk for each component, sigma 1 through sigma k. That's what the first conclusion lies here. And you can control the Morse index, this geometric thing now, of the limiting surface, sigma, from above by the Morse indices of these Allen Cahn critical points.
Before you said 0 to the other set.
Yes.
Here you said it's concentrated.
I just mean this definition again. Yeah, so they could be concentrating to something that has multiple components and possibly with multiplicity. The nodal set is concentrating in the Hausdorff sense, and the energies are converging to the correct thing. Yeah. Okay. So actually, yeah, let me pause here. Any questions about what this says? So this gives you, in some sense, the opposite direction of the construction that I was, and opposite direction of the construction that I was giving you earlier. Oh, incidentally, I should, for the construction that I was mentioning here of Picard and Ritter-Ray, this was a gluing construction when it was carried out. It's a beautiful result. Very recently, so my friend Alessandro Pegatti and Guido De Filippis have a variational way to prove this exact same theorem by their own kind of min-max construction in the manifold setting. Now, also, way before this result, in the Euclidean case, Juncheng here was able to construct with Manuel Del Pino and Michal Kowalczyk the analog of this for finite index embedded minimal surfaces that are non-degenerate in R3. Okay, so this is known in a lot more generality than I mentioned here. Oops. Okay. So going back to this, once you have critical points with bounded energy and bounded Morse index uniformly as I goes to infinity, then those will converge to the limit to some embedded minimal surface, but possibly with multiplicity. Okay. If you go above, so okay, what's with this dimension here? If you go above n equals 7, then you can prove that the limiting thing might not be a smoothly embedded surface. So Juncheng has worked on that with Frank Picard, where there's an example of something converging to something that is not smooth, but has a high codimension singular set. And this is indeed provable in this theorem here, but I didn't want to confuse the slides. And if you go below dimension 3, then things become subtle, and I'll come back to that later. It's interesting that things are subtler in dimension 2. But so are they in Angren-Pitts theory. So that is both reassuring and annoying. You can construct, if your epsilon is small enough, yes, that would be, for example, by this theorem. Yeah, you can have a min-max construction of these kinds of things for small enough epsilons. Yeah. Is that what you meant? Yeah. Okay, so I've made a big deal about multiplicities here. So a reasonable question is, could multiplicity occur? And if it does, then what can we say in that case? Because if you do get multiplicities out of these constructions, then one of the things that we were trying to circumvent that had then been a sticking point for Angren-Pitts theory, which was the Multiplicity-one conjecture, then we wouldn't have been doing any better. But turns out that in a three-dimensional case, we were able to circumvent this. And I'll come back to this. All right, so in the picture that I had earlier, could it be that you could obtain a limiting surface sigma with multiplicity at least 2? And so you can pose this question in broad generality. Can you have this under energy bounds or under energy and index bounds or whatever you would prefer? And if this kind of thing were to be able to happen, then we would be, it would make our life more difficult. Unfortunately, this kind of thing can happen. So this is another construction of Manuel Del Pino, Michal Kowalczyk, Juncheng Wei, and Jun Yang, where they proved that this kind of high multiplicity convergence can happen under these assumptions here. So if you have a manifold and some embedded non-degenerate minimal hypersurface and any prescribed multiplicity that you want, if you assume that the zero-order term in the Jacobi operator is strictly positive, so for example, if the Ricci curvature is positive, and if you assume that this surface, well, okay, let me come back to this. Then you can find a sequence of epsilon i's going to 0 such that you get convergence to that limiting surface with that prescribed multiplicity. Now, this second bullet point here about separating or not is it's kind of what you would, well, if you want to construct something that converges with an odd multiplicity, then because of how Allen Cahn solutions behave, then odd multiplicity would force you to be -1 on one side and +1 on the other side, which would mean a posteriori that this surface has to be separating. Whereas if you were to have even multiplicity, then your surface doesn't have to be separating for a silly counting reason like this. So all they're saying is that if you want to prescribe odd multiplicity, your surface had better be separating. So this is a very natural assumption. There's nothing fishy going on there. So unfortunately, you can have sequences of Allen Cahn solutions with energy bounds that are converging to a high multiplicity limit. So that's something that we do have to worry about, unfortunately. So the Multiplicity-one theorem that we have in 3 dimensions proves that, okay, so I didn't, I wrote down theorem here, but I didn't write the actual theorem. So let me write this one. So let's suppose you have, because I'll come back to it later. So you fix a 3 manifold and you have sequences of parameters epsilon going to 0, Allen Cahn epsilon I solutions with uniform energy and index bounds. Then, as before, this is what we know from before, actually, so let me keep it here so you can have it. Where is it? So then, there exist sigma 1 through sigma k and multiplicities m1 through mk such that you have convergence subsequentially, perhaps, to this union. And the Morse index is controlled from above. So our improvement to this theorem when n is equal to 3 is that we can actually understand this picture a little bit better. So we do still have this, of course, this still remains, but additionally, we know that these nodal sets now no longer just converge in the Hausdorff sense, as I was assuming here, but they decompose as C2 alpha graphs over the limit. So this kind of neck wouldn't be happening. You would get something like sheets as such. So this nodal set converge in the sense of C2 alpha graphs of the appropriate multiplicity to the usual limit. And then we have a dichotomy, which is what something will be squeezing some information out of later. The dichotomy is that if you get, for some reason, some limit that occurs with multiplicity at least 2, so if mi is bigger than or equal to 2 for some I, then even though these guys aren't quite minimal surfaces, they're so close to being minimal surfaces that you can extract a positive Jacobi field on this limiting object. So then sigma I, or its two-sided covering if it's one-sided, carries a positive Jacobi field. So in particular, its nullity is at least 1. Okay? If this is not the case for any of our i's, so if all the convergence, the whole convergence holds with multiplicity 1 for all components, then we have an inequality that is the reverse of this one. And the correct reverse inequality if you think about it hard enough, it has to include the nullity. And we prove that this is bigger than or equal to the limit of the index plus the nullity. Okay? So this is the main theorem that that was in the paper. Can you remind me how much time I have? So that's time. Okay. So let me tell you then. Let me tell you some the application and then some nice open problems. So one of the applications that we were trying to achieve was that when you combine the Gaspar-Guaracco min-max construction with this kind of result, you can prove that if your ambient manifold M3G contains no surfaces of this type, which have nullity, which is true for generic metrics G, then by a nice counting construction, you can prove that there are infinitely many geometrically distinct embedded minimal surfaces. That was a question of Yao. And subsequently, this is now known in much more generality using the Allen-Pitts theory, in full generality by work of Antoine Song, here, and previously in more special cases by Marcus Neves and then Joachimovic, Marcus Neves, Iri, Marcus Neves, and Xin Zhou. And I don't have time to go into the ingredients of the proof, but this proof required that we take and extend a little bit some very strong curvature estimates of Juncheng Wei and Kelly Wang, and prove with even more estimates this inequality right here, which is important in proving the geometrically distinct aspect of the minimal surfaces. The main, I mentioned that our result is for n equals 3. The only missing ingredient, because of recent work of Juncheng and Kelly Wang, the only missing ingredient is proving the stable Bernstein question for Allen Cahn solutions. So if you have a stable solution of the Allen Cahn functional in R4 through R7, is that a one-dimensional solution? If you have that ingredient, then you can use work of Juncheng and Kelly to plug and chug into our same proof and get the same conclusion. So the two-dimensional and three-dimensional cases are known for this, and we use the three-dimensional case being known, and the higher dimensional cases are false from 8 onward. And I was planning to say something about the two-dimensional case, but I don't have time. In the two-dimensional case, there's a big problem because a priori in the limit you get stationary geodesic networks, and if you use some other recent work of Juncheng Wei and Yong Liu, you can change this double whale potential W into something that gives you integrable systems in 2 dimensions and get limits that are actually immersed geodesics. And so you can circumvent this issue that still persists in Allen-Pitts theory. If you run Allen-Pitts min-max in 2D, you cannot prove that you get immersed geodesics. All you get is that you get stationary geodesic networks. That's unfortunate. But we can circumvent that by using the extra rigidity of the Allen Cahn equation with a slightly different potential. And what I wanted to mention is that there are some very nice recent parallel stories that are worth highlighting. Everything I've said was in codimension 1. What if you want to do higher codimension? Then if you're in codimension 2, there's this setup of the magnetic Ginzburg-Landau functional, where I've written it up, the definitions there, if you want to take a look. But the corresponding hope is that you can run a similar story and construct limits that are codimension 2 smooth minimal submanifolds. That is not yet known because one of the reasons is that we're missing a stable Bernstein theorem there. That's one of the key reasons, whereas we do have one in 2 and 3 dimensions for the Allen Cahn. So that's a very nice open question that I'm mentioning here, having a stable Bernstein theory for Rn within at least 3. There is also this other very interesting non-local minimal hypersurface approach to constructing minimal surfaces. This is more analytic in nature. So you change your operator from what I wrote down to the fractional perimeter of Kachoupoli sets. and that's a definition here. And then you try to send the fractional parameter s to 1. And all the objects you get from your various fractional perimeter min-max constructions, you try to pass to a limit, just like in the Allen Cahn sense, where you send epsilon to 0. Here you send s to 1. That's recently been getting some beautiful results. So the Yau type conjecture for generic metrics in 3D was recently proven using this approach by a graduate student at ETH, Florid Simon, or Florid Simon, I don't know how to pronounce it, he's Spanish. I am very confident that he can actually, because of some extra rigidity in the non-local setting, I think he might be able to do n equals 4 as well, but it's not there yet. But don't scoop him, he's still a graduate student. However, the higher dimensional cases are still open. So there are still missing ingredients for the cases 5, 6, and 7 to make that story work. And that's the corresponding stable Bernstein ingredient again. That's missing. So there are, while what I focused on was the Allen Cahn equation for codimension 1, there are these ongoing parallel stories happening in codimension 2 and again in codimension 1 with some extra rigidity using non-local minimal hypersurfaces. So this is a very nice field, and there's lots to do. So yeah, thank you for your attention.
Okay, so maybe one question.
Oh, that is Otis, not me.
Stable.
Okay,
Otis,
yeah.
okay.
Sure.
Okay.
But I can tell you what those do.
Yeah. What would it give some like implication for the Allen Cahn, some application?
We, including me now again, we try to think about that for a bit, but not yet. I mean, the techniques there are a little too intrinsic, and here, because you're working not one level set at a time, they don't quite apply. So not yet.
Okay.
Yeah. Yeah.
Okay, let's thank the speaker again.